Welcome back to Fat Mama Physics. In these video series, we're going to talk about the friction force. Friction force is not always bad, causing things to slow down, but also do us some good in helping us get a grip on certain objects and causing our bikes to move forward, cars, and even us when we are walking on the ground. So I do expect you to know a little bit about friction force, some of the basics, maybe if you watch some other videos and whatnot. I will do a quick recap on some of the key things I wish I would like you to know, definitely for sure, and the key thing I want to do in this video is to go over examples, as well as my other videos are all about examples. So without further ado, let's get a move on. So you should know that the friction force depends on two things. First is this little coefficient called the coefficient of friction. The coefficient of friction is it's a characteristic between two surfaces. So the larger your coefficient of friction, the rougher the two surfaces will be. When you take a look at two objects, for example, this wooden block on, say, the ground or dirt, concrete, or whatever, if you zoom in at the microscopic level, you will see these rough edges, teeth marks, if you would call it. And of course, the rougher the surfaces that they are, you can expect larger teeth, a lot of rubbish as this block is moving across the floor. The other property that the force of friction depends on is your normal force. So imagine this is how much the block is pressed up against this ground here. The closer that this block is pressed against the ground, the more interaction these two surfaces will have, causing the friction force to increase. Sometimes, and of course, this is also the reason why if you have a larger mass. If you have a larger mass, you have a larger Fn pushing down on the ground, resulting in a larger friction force, okay? The second thing I'd like you to know about is the difference between the coefficient of static friction and the coefficient of kinetic friction. Here I've drawn a few free body diagrams of a situation where, let's say you have a wooden block on the ground and you're slowly increasing your pulling force on it, and as you slowly increase the pulling force, the block isn't moving at this point. And the more you increase this applied force, at a certain point where you finally apply enough force, it starts to move, and you get the block moving forward at a constant speed, okay? So here at all points in time, this graph here is showing you, say, the applied force, and it's kind of assuming that either your block is not moving or going at constant speed, and this is telling you that, as it's changing over time. At the very beginning, as you're increasing the applied force, the force of friction is directly opposing the block, and it must be equal to your applied force even as you're increasing it. Otherwise, your block would be moving, right? It's at rest otherwise. So, and then when you reach this maximum threshold, you apply this threshold force, your block breaks the connection between its microscopic rough edges, and it starts to move. This breaking point, or this required force needed, is where you would use the coefficient of static friction to calculate that kind of like a maximum barrier force that you have to bypass. And that's where, and it's the only time that you can use the coefficient of static friction to calculate that maximum force that you need. And afterwards, you notice a drop-off where the applied force is much less. You need much less force to get the block to start moving. And you can think about that. You can try it out at home. You can try this out at home. You take something and start moving across the table. Feel it with your own fingers. Which one is easier? Is it easier to get the thing to start moving, or is it easier to get the object continuously moving across the table? Okay, so then when the object, or your wooden block here, is moving across the table, this is when you would use the coefficient of a kinetic friction. Kinetic meaning moving, and versus static meaning still or not moving. Okay, so that is the key difference between the two. And because of that, you will also notice that your static friction, the barrier force, sometimes if you want to think of it that way, is larger, meaning that your coefficient of static friction is larger than your coefficient of kinetic friction. Okay, so that's another difference that I want you to be aware of. So knowing these couple of things now, hopefully we can start with the examples. Alright, so let's start with example 1. Remember, I start an example and then finish it, and you do one yourself, okay? In this one, I will do actually both A and B for example 1, and you will do example 2. For example 1, you have a 525 gram block. Woohoo, this is in grams. Don't forget to put it in kilograms. It is originally at rest and is being pulled horizontally with a force of 3.3 newtons. That's your applied force. The coefficient of static friction and kinetic friction between the block and the ground are 0.67 mu s and 0.33 respectively. That's mu k. Calculate the acceleration of the block, okay? So first things first, we know this mass here is in grams. To convert it to kilograms, we got to divide that by 1,000, moving the decimal place 3 times. 1, 2, 3, giving us 0.525 kilograms. It's very suspicious that both the coefficient of static and the coefficient of kinetic friction are given in this question, and it's also suspicious that the block is originally at rest. So methinks that we need to figure out whether or not this block is going to even move with this 3.3 newtons. So the first thing that we're going to check for is we're going to check for the maximum amount of force we need to get the block to bypass the static friction to get this block to move in the first place, to be able to accelerate at all, right? So to do that, we need to use the coefficient of static friction here. I use the force of friction S for friction, static, and S for static friction. Okay, so let's, we have the mu S, okay? We just need to figure out the normal force. If a block is just at rest on a table, then we know that the force of gravity is going to directly balance out with the normal force. Since they are one and the same, we can use that to calculate the normal force. Since NFG is also mg, the mass of the block times gravity, so 0.525 times 9.81. Okay, we get 5.15025, so 5.15. So we got, and of course, we're going to save all those numbers. Then we know the FG, which is our FN, since they're one and the same. We are going to substitute it in this equation here with the mu s to figure out how much force we actually need. So that's 0.67 times 5.15. etc. newtons. We get 3.45 newtons, which 3.3 is just shy of, meaning 3.3 newtons is not enough to get this block to start moving. And because of that, this block will not move. The acceleration then must be 0. Okay, now we have a second question B. What is the acceleration of the block if the pulling force is 5.5 newtons instead? And notice 5.5 is definitely larger than 3.45 newtons, so this block will be moving, it will be accelerating, but this time we are going to need to use the coefficient of kinetic friction since the block will be moving now. And to start us off, let's draw a free body diagram of a block. And we know this time that the applied force is going to be much larger than the force of friction because the block will be accelerating, and also because the kinetic friction is going to be less than your static friction that we calculated above. We know that F net, so let's start off with F net equals ma, and our net force is going to be the sum of our forces in the forward direction, which I will be calling that the positive direction. That leaves us F net is equal to Fa minus the force of friction. I'm going to start to combine these two steps now, where I'm going to equate this to ma. Since F net is equal to ma, then I know that F net is also equal to Fa minus FFK, which then I can just combine the two F net equations. Everything's all equal. I will be left with just Fa minus FK equals ma. So I'll use this equation together instead. I like to solve my unknown first before I plug in all my numbers, so let's do that. I will be solving for acceleration, so let's divide both sides by mass. We know what Fa is, we know the mass, and then we just need to calculate the force due to kinetic friction, which let's do this one up here. So our force of friction here, we need the mu k, which we have in the question. We also need the Fn value. Now Fn notice it is balanced by Fg here, so they're one and the same in this question. And luckily we calculated that already in the previous question, which then we can just use in here. So let me just write this again. Now I can substitute the force of friction, kinetic friction, in here so that I have all of our values known in this equation. Okay, substituting all our values in, we get... Okay, so then putting this all in our calculator, we get a whopping 7.23 etc. meters per second squared for our acceleration, and which I will round that to 2 sig figs, 7.2 meters per second squared in the forward direction, hence the positive sign. Okay, so that's the question here. So notice a key thing was to double check whether or not you have enough force to bypass the static friction, and if you can bypass the static friction, then you can go ahead to calculate the acceleration of your object. So, which leads us to the next question, which I will give you a chance to do yourself, which is very similar to the last question. So good time to pause the video for you to try. And now I will go ahead and do the question and replay the solutions in fast play. Let's start off with labeling a few things. We have the mass of our bag, the applied force, and the coefficients of friction. So first we need to check whether or not the force of 98 newtons is bigger than the force of static friction. And to do that, we need to know Fn. We can calculate Fn by calculating Fg, which are the same because the vertical force is balanced. And we get 245.25 newtons. So then if we put it in here times the coefficient of static friction, we get 95-ish newtons, which is less than the force that we are applying with. So that means the bag will move. Let's do a proper free body diagram here, where we're going to use the coefficient of kinetic friction instead. With the forward direction being positive, we write our F-net equation, in which the applied force minus the force of friction is going to be equal to ma. Solving for acceleration, dividing both sides by the mass, we get the following, and we can then start to substitute everything in, and in this case, we're using the mu of kinetic friction times the normal force, and putting everything into our equation, we get the acceleration is 1.8 meters per second squared in the forward direction. Okay, and here are our solutions. We find out that poor Richard does have enough applied force to break the camping bag from the clutches of the static friction. So then we went on to moved ahead to calculate the acceleration, but this time using the force of kinetic friction and the coefficient of kinetic friction instead. Okay, so hopefully these videos gave you an idea of how to tackle some of these problems, how to set up the problem, and that you learn a little bit about friction. Okay, so thank you for watching. Good luck with your practice. Fat Mama Physics. Sign.